In this example, we're going to be analyzing a simply supported beam using a 3D CAD model and ANSYS solid elements. So we worked this example before using beam elements, where we had a simply supported beam made of structured steel that has a span of 10 meters long and is loaded at its center with a 1000 Newton. We have it here at point C when we use the beam elements, and we had a pin support at A and roller support at B. This is a mathematical idealization for the beam, but in real life, a beam is a 3D and is going to be supported. Either if this is a steel beam, it could be welded or it could be fastened to some support or could be sitting on some sort of a support. So one of the important things we want to understand when we go to 3D modeling is that each point in 3D has only 3 degrees of freedom. In comparison to beam elements, each vertex represented a face and had 6 degrees of freedom, 3 translational and 3 rotational. With solid modeling, we are working in 3D already, and each point display state is going to be represented by 3 translational degrees of freedom. There are no rotational degrees of freedom for a point because a point is a point. Another important difference you're going to notice that we do not have anything like a simply supported because we do not have these rotational degrees of freedom. We are only dealing with translation in X, Y, and Z. We are not going to apply the constraints to a vertex, but we're rather going to apply the supports and load to faces. We're going to apply the support and loads to faces, not vertices and not edges. So what are we going to be doing in order to capture the behavior of that pin support? To our understanding, this pin support allows for the rotation, but does not allow for the translation. And when I say allow for rotation of that front face. As you see here, this green line show that that face can rotate. In real life, that's gonna be the support is gonna be applied to a very small area or a face. So in my modeling, when I'm creating my CAD model, I have to prepare for that and create that small face where in real life the support is going to be applied. So if I think of this beam as sitting on some sort of supports, I would like to create this area, an extra area, small here that you see in purple, and make sure to fix that small area in 3 translational degrees of freedom. Likewise, at the roller support, I'm also going to create this purple section where I can apply the constraint to that region. Also, when I look at the load, a load cannot be applied to a point in 3D, so I have to create a face or an area. So even if that force is applied to a very small area represented by a point in beam modeling using beam elements, in 3D, there need to be a face even if that face is small. So when we create the geometry, I want to see like 3 regions: the purple, the blue, a purple, blue, and another purple. So we're going to be creating like 5 regions. Using Design Modeler, we can create these using 5 different extrudes. We can do that. Or we can create regions or surfaces after we create that. Just for simplicity, I'm going to do 5 extrude in Design Modeler of this rectangular section that is 10 by 20. I'm going to keep my beam oriented along the x-axis. and we should be able to get results that are comparable to what we did earlier. One other point that I would like to make is that when I'm using 3D modeling, I cannot draw shear and moment diagram because ANSYS is no longer doing beams. But I can look at all different types of stresses, strain. I can look at the deformation or the deflection of the beam at any point. We are still going to need to restrain all rigid body motion. When I say rigid body, it's for the entire beam. So we need to make sure the beam is restricted from translation in the X, Y, and Z. And also the beam as a rigid body is not going to rotate about the Y and Z and the X axis. So we're going to run into the issue if I supported at these two faces that the beam still is free to spin if a torque is applied. If that's the case, I'm still going to need to apply a rotational degree of freedom of a face, and we can do that using something called remote displacement, because there are no rotational degrees in freedom when we're using solids. And again, we're not going to be able to draw shear and moment diagrams. So these are some of the important difference moving from beam modeling to solid or 3D modeling. So let's start working on this problem. Here, I'm going to start with a new ANSYS Workbench project. And the first thing I want to do is I want to go to my units and make sure I'm using the metric. So I have meters and Newton. I'm displaying the values in the project unit. I'm going to save my project. So I'm going to come here and do a save as. And I'm going to put it in my ANSYS folder. And I'm going to call it beam model using solids. Next, I'm going to create an analysis system, a static structure. So I double click. We are using structure steel. So I go to engineering data. I have my structure steel material defined. I have the modulus of elasticity and I have my Poisson's ratio. So we're good with that. I'm going to toggle back to the project and we're going to continue to use design modeler. So right click and I should be able to go choose a new design modeler geometry. This will launch design modeler. I can turn on my 3 default planes. Again, I want my beam to be oriented along the x-axis. So I'm gonna use Sketcher to sketch my section on the YZ plane. So I'm gonna go to the YZ, select the YZ plane, and I'm gonna choose a new sketch. I want to be looking to the YZ plane, so I'm going to select this x-axis. Looking at my ruler, I need to zoom in. And now I'm going to move from modeling to sketching. And I want to sketch a rectangle. So I can go select a rectangle. And I'm going to start here with a rectangle that is not properly oriented. And we're going to see how we're going to fix that. If I want the centroid to be the origin, I'm going to go to constraints. I'm going to select the axis of symmetry. That shouldn't be. Okay. I'm gonna select the first point or edge, second, and here we go. Now I'm gonna put my dimensions for the base and for the height. And we look at our problem. I have a rectangular here that is 10 centimeters by 20. So V1 is the 10 centimeters, so that's the point 1. And H2 is the point 2. So here is my section. I'm going to toggle back to modeling. And if we like what we see, we can generate it. Here is my sketch. And this is ready for an extrude. So I'm going to create an extrude in the normal direction. And I'm going to go here with the depth of 0.1 meter. This is the very small area to accommodate the support. And I'm going to click generate. So here comes a very small portion. Next, I'm going to create another extrude. And in order to do that, I have to have a sketch that I can extrude. So I'm going to create first a new plane. So I can come create a new plane. And this plane is going to be using a face. And I'm going to select the front face here.
Professor, how much did you extrude by?
0.1 meter. Okay. Apply, and I'm gonna generate, and here is my new plane. On this new plane, again, I'm gonna sketch. So I have here plane 4. I'm gonna create a sketch. Keep it simple. We're gonna look here in the X direction. And this is just gonna be constrained to the existing sketch. So I'm gonna move to sketching, and I'm drawing a rectangle, and I wanna make sure I go at the corner, I see the letter P, and I wanna see a letter P again. So my rectangle or new sketch is fully constrained. We're gonna generate it. I'm gonna go to modeling. And I'm gonna sketch here. Sorry, I'm gonna extrude. And I'm gonna use sketch 2. Apply. And this time I'm gonna extrude a depth of 4.9 meters. So what I'm doing here with these 0.1 and 4.9, I'm allowing the distance between the center of this extra region to the midpoint to be exactly 5 meters. I'm gonna show you that when we're done. And I'm gonna generate, and here comes another region. Next, I'm going to create a new plane, and it is from the face. I'm going to select the front face here, apply, generate, and here comes plane 5. On plane 5, I'm going to do a sketch, and again, we'll be creating a sketch for a rectangle that is fully constrained to the existing one. So I'm going to go to sketching, rectangle. I want to see the letter P. I want to see the letter P, fully constrained, generate. I go back to modeling, and here comes sketch 3. If we want to look at it in 3D, that's where we are. we are going to extrude, and I want to allow for an area or a region to apply my 1 Newton load. So I'm going to extrude, and for the geometry, I'm going to pick sketch 3, apply, and I'm going to extrude a 0.1 meter. Generate. And here comes this tiny face where we can apply the load. So now we have 3 extrudes. I have 2 more to go. So for a new plane, so that's plane 6, and I want to do from face. I'm going to select the very front face, apply, generate. Here is plane 6. On plane 6, I'm going to create a new sketch. And I'm going to move to sketching. And I want to draw a rectangle. I want to see the letter P. To see it clearly, I'm going to choose the X direction. So now we're looking into it. So I want to come here and see the letter P, go to the other corner and also get the letter P, fully constrained. I don't need to put any dimensions. Generate. Here comes my rectangular section. I can see it as sketch 4. We want to extrude that 4.9. So I'm going to go with an extrude. And I want to select. This is my fourth extrude. Oh, this should be 4.9. I'm sorry. Generate. Okay. So now we have 4 extrudes. We are missing 1. And for our last extrude, I'm going to create a new plane from face. And I want to select the front face. Generate. Here is my new plane. And on this plane, I'm going to create a sketch. So that's sketch 5. And the last one. I'm going to toggle to sketching, draw a rectangle, point. Let me see the letter P, fully constrained, generate. And if I go back to modeling, I have my sketch 5 on plane 7. That's the one we want to extrude. Apply. That's sketch 5. And I'm going to extrude this 0.1 meter. Generate. Okay. So now it looks like we had done all the extrude correctly. But if I look carefully at this, I ended up with one solid. And I really want to show you, if I take this solid and to ANSYS mechanical, so if I go back to Workbench and double click, I have a geometry. I double click here to start mechanical. We look at our geometry, and I have one solid piece, which I really could have created just with one simple extrude. The point I'm trying to make here, that if I did all this effort and I come here and try to find the faces to select, I only have one top face to that. So with this extrude, even though we have 5 different extrudes, we did not end up with the regions that we needed to apply loads and support. So before we proceed, this is the point I want to make in Design Modeler. We want to come back and make sure we use add frozen. So every time I'm doing the extrude past the first extrude, when I go to the second extrude, I want to change that from add material to add frozen. And generate. I want to do the same with extrude 3, from add material to add frozen. Generate. Extrude 4, from add material to add frozen. And we're going to see the difference. Generate. And for extrude 5, from add material to add frozen. And generate. Now we have 5 distinct bodies with the faces that we need to apply loads and constraints. So it is really important when I'm creating the geometry. I'm not just creating a CAD model, but I'm creating a CAD model for simulation. So I want to make sure I have the features that are needed for that modeling or finite element analysis. We want to be careful. I ended up with 5 bodies, but also 5 parts. I do not want to leave them as separate parts. Yes, ANSYS is going to attempt to create context, but if possible, I want to avoid that. So I want to make sure to select my 5 solid pieces and do a right click and choose to form a new part. Now I have one part, but I still have my 5 distinct solids. In order to reflect that change into mechanical, I can simply go to Workbench and click Update Project. Now, if I go to ANSYS Mechanical, we see that the geometry has been updated. I have a part that is made out of 5 bodies, but there is a question mark here, and it looks like we need to visit our geometry to make sure that everything is okay. So when I go look at the geometry here, we have our solids and we formed a new part and everything looks like a green check mark. If I come here to my part, it's made of structured steel. Oh, you see when, it is the material property. So I want to make sure that structured steel is assigned to the entire part. Because one of the reasons you may be creating these multiple bodies, should these bodies may be of different material. I can go to each solid and assign a different material. But once I assigned it to the part, the children are going to follow because all these solids are children of the part. So now I have this green check mark and we are done with importing the geometry from design modeling into ANSYS mechanical. Next, I'm going to go to my mesh and I want to put in a mesh, and we want to make sure our mesh looks good. So I'm going to go with the default settings and click generate, and let's see what we get. So we have here a decent mesh. It's not too fine, it's not too coarse, but if I want to refine the mesh like we did before, I can go to the mesh and choose sizing. And I want to select the bodies, and we have 5 of them. So I want to make sure to capture all of them. Apply. So 5 bodies selected. And the default size here was 0.5 meter. I can come here and change that to a 0.2. But actually, let's make it a 0.1. And I'm going to click generate. If we look at a mesh, here we have a more uniform mesh through the pieces, through the different bodies. Now, as we're looking at this beam, I want to emphasize that the reason we have this gray is to be able to apply a support to represent how the beam is going to be supported at the front end. The reason I have this green area is to apply the loads. And again, for this green grayish area is to apply the roller support at the other end. If we look at the span of the beam, this is center to center. We have 5 meters from the support to the load and another 5 meters from the load to the roller support. So this is how we're trying to capture the behavior of that simply supported beam. Next, I'm going to go to static structure and start applying the constraints. And as we discussed, I'm going to be applying a fixed support to that small face to represent the pin support. So I'm going to put a fix, and I want to put this fix to the bottom small face that you see here. So this is my bottom. So I'm going to select the bottom. I'm going to say apply. So that's a fixed support. That's not going nowhere. On the other end of the beam, I do have a roller support. And what a roller support does, it allows the beam to slide in the X direction. And I can do that by using a displacement support. And I'm going to pick the bottom face, apply. And I want to make sure that the X component is free, while the Y component is a 0 and the Z component is a 0. So now I have my 2 supports, a fixed and a displacement. Next, I want to apply my load, and we're going to apply it at the top of the beam going downwards. So it's going to be applied in the negative Y direction. So I'm going to go put a force. I'm going to select for the geometry, I'm going to select the top face. I'm going to apply, and I want to define the force using components, and it is acting in the Y direction, and it is a minus 1000 Newton. Let's do a quick check. If I go to static structure, I have here my fixed support for my pin. I have my displacement support for the roller, and we have our force applied at the center of the beam. Okay. Let's try to run the analysis. So if I come here and click solve, ANSYS is going to attempt to run the solver, building the mathematical model, solving the mathematical model, and it looks like we have a solution. So let's look and see if this beam is behaving as we expected. So I'm going to go to the solution. First thing I want to check, results, deformation, and I want to look at the total deformation and solve. And look at this. Let's see what our beam is doing. what we can observe here is that the beam is not perfectly behaving like the simple support model with a pin and a roller, but rather the way it is being supported using solid model is giving it a bit of a fixity at the ends. So you see the face, we still get slight rotation. So it is not fully fixed, but it is not fully free as well, because now the constraint is applied to an area. But I would like to point out that using solid modeling, we may better capture a behavior of a real life model. Because in real life, the support is not applied to a point, but is rather applied to a face. So when we use the beam element, this is using mathematical modeling to do something simple to try to capture a behavior of a 3D part or an object. Okay. So if we think this is acceptable, and yes, if you compare the deformation, they may be slightly smaller than what we got earlier. But let's check for the reactions. If I go to probe and look at a force reaction, I'm going to start with at A, fixed support. Now I'm going to put another probe to look at the force reaction at C, at the roller support, and put another probe and look at the deformation. And I want to capture the deformation at midspan. And again, I'm going to put the probe to the face at the bottom. I'm going to say apply. And I want to look at it in the Y direction. And let's click solve to look at these numbers. So let me first look at the reaction. I'm getting a 503 Newton at the left support, and should be 497 at the right support. So it's not perfect. Again, there is this numerical error. Again, if you look at the percent error, 3/500. So this is definitely less than 1%. So we are within an acceptable range. If we look at the deformation, again, I would assume this is going to be more conservative than what we found earlier. We are looking here at a 0.46 millimeters. 0.46 millimeter. I can look at the stresses in the beam. So I can go results and look at stress. And again, I want to look at the normal stress along the axis of the beam. So I pick the x-axis, and that would be a nice one to look at. When click solve, please pay attention to that, because now we see, if I come here to where the moment is max towards the center of the beam, we can see really the distinct color showing tension at the bottom, compression at the top, zero at the neutral axis. And as we move to where the moment should be a zero, we almost have zero here, but I want to point out the singularity errors as we move from the fixed region to the free region. We have a very elevated stress at the top here, where really we should not be getting a high stress at this area. So please realize that this is one of the things we have with the numerical solution, that we have these high stresses in areas close to a fixed support where they should not exist. So if I'm really trying to find the maximum stress in this beam, even though I have this elevated stress, but I'm not going to be very much concerned about it based on my understanding of the behavior and how I'm applying my constraints. When I'm using solid models, I can also look at von Mises stress, which we can use with the failure criteria. So I can come here, go to the solution, and go to results. I can do a stress and look at equivalent or von Mises stress. And that's going to be all positive, but it helps us identify where failure may begin. And if I come here and I want to see the maximum stress, again, I would not be concerned about this elevated stress at this sharp corner. And if I look at where I expect the maximum stress to be, we'll be going close to the center of the beam. And if I use my probe, I have here about 2 million psi at the top, and should also be similar at the bottom and the top. So this is the more realistic maximum stress, and not that red one that we are seeing at the edges. Okay, and this is part of the limitation, or rather the errors that we may inherit with the nature of the numerical solution. So with this, we were able to analyze that beam, capture the behavior of it, the way it is being supported, assuming it is supported at the bottom of the beam towards the two edges, and it's loaded at its center.